we started this example, so I'll just start it all over since we didn't get very far. It says we have a small cart, 100 grams, is moving at 1.2 meters, let's say to the right, on an air track that when it collides with a larger cart at rest. That's exactly what we were talking about. So what you're seeing here is that we have a projectile cart whose mass, M1, is 100 grams, which is 0.1 kilograms. And we have a target cart, which is M2, and that is this is 1 kilogram. So right away, you can see here is that M2 is equal to 10 times M1. So we can actually then say, so this is not the example that we looked at here, but we can clearly see that in this situation, M1 is much, much smaller than M2. So when I think of my picture, I should be thinking of a massive target right here. This is the example that we want to look at. So now let's look at the details. So if I look at the details, then I have a very similar situation going on. So what do I see here? What I know here is that I have a system. So what is my system here? My system is that I have a target, a projectile. This projectile is coming with this amount of momentum, which I'll call 1, and it's going to run into a target that's at rest. So when I look at this thing, what I'm seeing here is that the first thing that I'm going to do is I'm going to identify my system. So if I identify the system here, then I look, are there any forces acting other than the collisions? So the impulse equals to 0 implies that the only forces are internal and no external forces exist. Therefore, the momentum must be conserved. So what do I mean by the momentum? It means that the total momentum of the system, which in this case is going to be the momentum of block 1 plus the momentum of block 2, this guy has to be a constant. That's what the 0 impulse implies. So now I have my before, and now I can set up my afterwards. So therefore, these blocks have to behave in such a way that this is my picture. So from this picture, we now want to get numbers from it. So let's go do that. So our picture then says, we would expect that block 1 is going to come back. And because the mass of 2 is much, much bigger than 1, we would expect that roughly the final momentum of 1 should be roughly equal to that of it initially. And this is things that we want to check, right? And then afterwards, we would expect here that the momentum of the bowling ball should be quite large, even though its speed is going to be small. Why? Because the mass of 2 is very, very large. but its speed is going to be small. But the combination of that says that the lion's share of the momentum must be going to the right. So here we go. I'm going to set my positive direction here. I'm going to set my negative direction there. So then I'm now going to draw a momentum bar diagram to write out the correct equation. Well, so by drawing the momentum bar diagram, not only are you getting the physics, but it's also writing the equation for us. So here I go. So what do I expect? I expect that this is the momentum going to the right. It has that amount of momentum. The momentum of the block for 2 is initially at rest. So now this is going to be our constant line. So now what happens afterwards? So then afterwards, we expect that the momentum of block 1 to be somewhat comparable, but in the opposite direction of its initial momentum. So then if I look at the momentum of the bowling ball, it should be moving in this direction, and it should be the largest here. So now this tells me here that again, this side here is positive, this side here is negative. So now let's write out the equation. So if I write out the equation, remember this is my constant line. My equation then reads that P1 initial plus P2 initial must equal minus P1 final plus P2 final. That's what it says right there. And we know that this has to be 0 since that is the case here. So now what I want to do here is that I want to go in and I want to look at our numbers here. What is our numbers? So conservation of momentum, right? This is what conservation of momentum says. It's from the bar diagram. It says this, but let's look at this. So from here, what we want to do here is that we want to check our physical understanding. And what do I mean by that? Well, what we said is that the momentum of P1 initial should be approximately to P1 final. So is it? And we expect that the momentum P2 final to be, I don't know, I'm going to say much larger than P1 initial. Let's see if this is the case. So let's calculate these individual numbers here. So here we go. So now let's calculate individual numbers. So typically I would not do this, but I'm doing this because I want to be able to show you if this picture is correct or not. So the first thing that we want to do is that we want to calculate the initial momentum. So then it's got to be M1, then it's got to be V1 initial. Now, if you go and you look at what it says here, here's what we know. The mass of 1 is equal to 0.1 kilograms, its initial speed is equal to 1.20 meters per second. So if I calculate that number, I'm going to get a value that reads 0.1 kilograms times 1.20 meters per second. This will then give me 0.120 Newton seconds. And this is the initial momentum right there. Okay? So this is what I know right here. Now let's go calculate P1 final. Now P1 final is going to have a negative number. And you could see there's my negative number right there in the conservation of momentum because it was going to the left. So here's what the data tells us here is that P1 V1 final, again, we know what the mass is, but what is the speed? So note, I'm not writing down, excuse me, I'm not writing down the sign. So this will be 0.85 meters per second. So then if I multiply this out, I'm going to get 0.1 kilograms times 0.85 meters per second, which will then give me 0.085 newtons second, and that's going to be the magnitude of P1 final. So are these guys close to each other? Yeah, roughly, right? This is like 0.12. This is like 0.09. So I would say that they're roughly, so if you were to go to 1 sig fig, they would be the exact same value. So I would then say that we could roughly claim to 1 sig fig that P1 initial, the magnitude of P1 final, that they are approximately the same and equal to 0.1 Newton second. So I would say that if we come back to our statement back here, that if we threw a golf ball at a bowling ball, it's going to roughly come back with the same momentum. So I would agree with that statement. So the numbers seem to agree with that. Now, I can't calculate the momentum of 2 yet because that's what the question is asking. So now, so far, our picture seems to be agreeing with what we claimed. So now what I want to do here is that now let's calculate momentum P2 final. We really want the speed, but let's calculate the momentum P2. So here's where we go. So from conservation of momentum, we already wrote this out. We said that we had P1 initial plus P2 initial has to equal P1 final with the minus sign plus P2 final. And we already know that this guy starts at rest. So now I'm going to solve for P2. So I got to bring P1 over. So this tells me here is that then P2 final is going to be P1 initial plus P1 final. Look how important it is to get that minus sign right. These two add, they do not subtract. So if I put this out, look what I get. I get 0.10 plus 0.085. And so if I add these together, I'm going to get 0.205 Newton second for the momentum P2 final. So now let's go back to our picture. Does this agree with the bar diagram? What we said in the bar diagram is that the lion's share of the momentum was carried by the momentum of the bowling ball, right? That's what we were saying right here. So if you look at this thing, I can then see that the momentum, this is of the larger block, is 0.205 Newton second versus the incoming momentum, which was 0.120 newtons per second. You can clearly see that it's larger. In fact, how much larger it is turns out to be almost by a factor of 2. So if I look at the ratio, so this tells me here that if I look at the ratio of this, the momentum of 2 plus what's coming in, this turns out to be 0.205, 0.120, and this is 1.71. So this is, to 2 sig figs 2 times, right? So to 1 sig fig, P2 final is twice as large as P1 initial. So we are seeing that the lion's share of the momentum goes with the bowling ball. So our picture is pretty accurate, actually. So I calculated these numbers just to show you that this picture right up here, right? This is our picture. This is an important picture. It's not something that we are sort of like, I want to copy this and bring it down here. So if I was to really draw my momentum bar diagram and scale it, what would it look like? Well, what it would look like is this momentum actually has to be a little bit higher. So, so this guy is, right? So it has to be, to 1 sig fig, it would be higher, but it's probably more something like about right here. That's about how accurate that guy is. That's a really accurate picture. You couldn't get that from the numbers. So now that I'm showing you that these bar diagrams really do make physical sense, what we want to do here is that I want to go back and I want to resolve the problem. So I want to go back and resolve the problem the way you should do it for problem sets and quizzes. There's a lot of conceptual stuff in here, just showing you that those bar diagrams are very, very accurate. And so what I'm going to do here is that I'm going to go right back to here. Using our bar diagram, this is what we wrote. right? This is what we wrote. So we don't want to check the physics anymore. We now just want to use a mathematical process. So what do? I then want to replace the momentums with mass times velocity. So if I do that, I'm going to get m1 v1 initial. This is going to be minus m1 v1 final plus m2 v2 final. So now, solving for v2 final, like it's asking, you can see here is that I got to take the momentum p1 final to the other side. So then I'm going to get m1 v1 initial plus m1 v1 final. Then on the right side, I'm going to get m2 v2 final. Now look what I'm going to do. I'm going to isolate the mass so I do less calculations. And now I divide both sides by m2. And if I divide both sides by m2, I'm going to get v2 final is then going to be m1 divided by m2 times the quantity like this. And remember, there's no sign on this guy because look, where did we put our sign? That's our negative sign right there. We added the sign there. Don't put a second sign in there. So then if I just put in my numbers, then my numbers suggest that this guy's going to be 0.01 kilograms divided by 1 kilogram. And then my speed here is going to be 1.20 plus 0.85 meters per second. And so this will then give me a value of 0.205 meters per second. And that's the final speed of block 2.